welcome to the second session on our project 2. So, in the last class, we were discussing about the problem of heading angle control. So, uh, I hope you have gone got time to go through this. I have uploaded the PDF, the problem statement. So essentially, what we are doing is we are modeling the lateral dynamics of a uh, uh, in bicycle model and getting the transfer function and designing a controller to respond, make the system respond in a desired way. So in the last class, we reached till constructing the state space model and how to get transfer function from that. In this class, we'll see how we'll design the controllers, the proportional and PI, proportional plus integral control. And as discussed earlier, we have two cases. One is with steering dynamics, and one is without the steering dynamics. Okay, steering actuator dynamics. So now I'll start sharing my screen. Okay, you're able to see this PDF file, right? This is what I have.
Visible, Abhinav.
Okay.
Visible.
Yeah, this is what I have uploaded in the Google Classroom. So, yeah, we have covered all this. Yeah, coming to what you're supposed to do and put in the report. So first, you will you will derive the governing equation and get the transfer functions that I've already explained in the I have already shown how to do. So you can you need not go in much detail of every step. So you can you know uh, maintain it in a crisp manner how you get the transfer function and for the delta and then the theta. Okay, then coming to the part B, so open loop response. So here this question says first plot the heading angle response. So without putting any controllers, we just wanted to see how the system is responding. So we'll plot the step response for a 20-degree angle input, uh, and then the second part is not required. So you don't have to do the Bode diagram. So
நாளே கிடையாதடா.
someone is not speaking, please mute your mic.
Sorry.
Yeah, no problem. So here this border diagram is not required. We have already got the transfer function and the other required things we can get from the route array. So here in the part C, you will find the closed loop transfer function and you will construct route array and to find the ranges of kp, and when designing the PI controller for finding the range of kp and ki, you will construct the route array and apply the route stability criteria to get the ranges of kp and ki. So in today's demonstration, in today's session, I'll directly go to the the RL tool and start designing there. But when you do it, you first construct the route array and then get the ranges. So that will give you an idea of how you choose the values. All right. So next, for the designing of the stability criteria, designing of the controllers. So these are the constraints we have. So the desired heading angle is 20-degree, and the maximum peak overshoot is less than 10%, steady state error less than 5%, and the maximum controller output is less than 40-degree. So once we get this, once we obtain the required output, we plot the closed loop response, right? So part D is when we include the steering actuator dynamics. All right, so I'll switch to the MATLAB window. Yeah, uh, output is visible now. So the actual transfer function, once we derive the uh, transfer function from the state space model, you will substitute the given data values like the mass of the vehicle, CF, CR, and all those things, and get the exact numerical values. So in this demonstration, I'll just show you. I'll take a similar transfer function with values rounded off so that you'll get an idea. So I'll create the transfer function. I suggest that if you are able to do along with me, that would be great, so that if you encounter any errors and all, you can ask.
Yeah, yes, sir.
So I
We'll do it.
okay. So this is an approximate transfer function. So you will obtain the exact values when you substitute the parameters here. I took the values, approximate values here. So now so this is a transfer function without any steering actuator dynamics. All right. Now we'll go to the RL tool. Are you able to see this control system designer window?
Yes, sir. Yes,
Okay.
yes. I will.
Fine. So here at present, this is our response with the given poles and all. Now we will create our constraints. So what we'll do, we'll put the design requirements. Yeah. So first is our peak overshoot. Peak overshoot we want to be less than 10%, right? Right. And and what's the other one? We have our steady state error to be less than 5% and maximum controller output to be 40%. So 40 degrees. So for this, so our desired heading angle is 20 degrees. So here if you see the step response plots for a step of 1. So in order to make it for the step of desired angle, so you can see that in the architecture, you see that the input block. Yeah. So here R is our reference input. So F is what makes allows us. This is the gain block to allow us to, make the step from 1, which is the default value, to any desired value. So now from 1, I'll change it. So double click on F. So so that you can change the value. This opens the compositor. So 20 degrees. So you'll have to change it to radians. Okay. Okay, so it won't calculate. I'll, uh, so here you'll put the value in radians. So I'll convert it.
It's 0.348.
Yeah, I'm calculating the final value. Yeah, so around, okay, yeah, 0.349. Sorry, 0.349. Right. So this will uh, this will make our system respond to this input, that is the 20-degree step input. All right.
Abhinav, just one question.
Yeah.
This F block in that configuration was what actually?
So if you see in the architecture, you can see that
Yeah,
we are giving R as our reference input. So
correct.
by default, our step response responds to a step input of 1. So
Okay.
this F block is, we can put a gain here at the place of F, so that 1 into this value, that is what
Okay.
the final
Understood.
step value.
Understood. Yeah. Got it.
Yeah.
So for that, we are currently multiplying the angle in terms of radians. That's why that conversion happened.
Yeah, that's what. That's all.
Okay. So since in the question it's given that we are incrementing steering angle by 20 degrees, so we are giving it in radians and that's why it is 0.349.
Yeah, that's what. This is
Okay.
0.349 radians, that is 20 degrees. So we are giving a step
Okay.
input of 20 degrees essentially.
Got it. Thank you.
So now we have the and we can also track the final uh, response by, because we have a constraint on how much the value can increase up to. So it says the value should not go beyond 40 degrees as well. So that we'll monitor by putting the characteristics steady state. So the steady state value, so 40 degree is essentially double that of 3.49, right? So here we can monitor whether the final value is going beyond. So now we'll first design the P controller. For the proportional controller, which is the block we will alter. So where do we add the KP? Do you remember what we discussed for the first project? Hello?
Abhinav, your voice was slightly breaking. Can you repeat again?
Oh,
Sorry.
okay. So here first we are designing the KP, the proportional controller. So we want to add the gain KP, right? So which block
Correct.
do we change or add the gain? Which block?
I think we added a real zero.
We have to add a real pole, real zero, right?
Do we do that for KP? So what
KP
is
is
the
1 by S, if I'm not wrong.
1 by S block.
what does KP do? What does the proportional controller do?
Is basically what I'm going to say, giving a constant multiplying gain in that sense.
So we are giving a constant, so it multiplies the error with a constant value and gives the input, right?
Correct.
Right.
So in the architecture, if you see, yeah, so here this is our controller. So if we are multiplying with a gain, so what is that the transfer function of that operation? It will just be the value of gain, right? So we are not,
Correct.
yeah, when we are adding the integrator, there is ki by s, so that's why we add a pole.
Correct.
Okay, so when we add a proportional controller, we are just multiplying the error coming. This e signal is the error signal. We are just multiplying the error signal with the gain, with a certain numerical value, and giving that as the input. Clear? So for that, so which, according to this architecture, which block do we change?
C block.
Yeah, C block. So we'll monitor the C block. So now the gain is 1. We have not added any value of kp, so the gain is 1. So now we'll see what how will the kp change as we change the poles, right? So as I change the poles, so the do we have a constraint on settling time? Steady state error. Okay. So
Abhinav, I think I've lost your screen. I'm sorry.
is my voice breaking or something?
So in between it is breaking, sir. After that it will come back.
Oh, okay. Sorry for that. So essentially now I'm shifting the poles to see what. So I want to increase my, essentially when we design the controller, with these constraints we achieve the most optimal performance, right? Optimal performance in the sense we'll achieve the, we want to get the least possible rise time, settling time, and the peak overshoot constraint is already given. So we are shifting the poles so that we can add the kp. All right, now the value of kp is we have, because of this constraint, you see this region is, we cannot enter this region. So if we go into that, the peak overshoot, just a second. Oh, 10% is extremely high.
Abhinav, are you speaking something? I'm
No,
not
no,
able to
no,
listen.
I'm not speaking.
Sorry.
when you shift the poles, be careful that you don't shift these lines. Okay, they can move by themselves when you drag and all. So be careful that you don't change. I'm just saying that when we put the uh, peak overshoot constraint, right? So it is the peak overshoot is below the overshoot is actually not happening, but even in in this region, it is showing that uh, the curve is not overshooting, but it should overshoot beyond the 4% value when I go into this. So that's what I'm checking. Just to give me a minute. Okay. I'm sorry. Okay, here the transfer function. No? The transfer function I have created a much. I made an error here. Sorry for that. So the transfer function is this. I'll close this window now. Just give me a second. Yeah, sorry. We'll go back. Yeah, so by mistake I typed 170 instead of 1720. That's why the system is behaving so sluggishly. So now I think it'll. Yeah. So now first step is to change the F block so that my gain is. I give the step to 20 degrees value. So what is it? I think 0.349 is it? Okay. And then okay, now coming to the C block. Yeah. So I'll give the constraints of the peak overshoot. It is 10%. Okay. Or the 10% value given is actually too high for realistic purposes. So what we'll give is we'll give it 4%. Yeah. So please make this change in that PDF. So one is that the Bode plot is not required, and next is the peak overshoot should be less than 4%, not 10%. Sorry for the errors. It's actually the question paper for the last year, but I couldn't change it. Sorry.
Noted, no problem. Yeah, noted.
अभिनव एक रिक्वेस्ट है मेरा
हाँ, yes.
बेसिकली आई रिक्वेस्ट बेसिकली
Yeah.
आई एम सॉरी टू जस्ट इंटरप्ट इन बिटवीन आपने जो पिछली बार लास्ट टाइम यू हैव written the equation, if I'm not wrong, on the
Huh.
file. So
The
if you have
transfer
the
function?
page, yeah. If you have the page available, can you go there for 2 minutes? I'm sorry to just
Yeah.
trouble you. No, not like that. When you handwritten some notes, is the available with you?
Roshan sir, you're asking about the state
This one?
space conversion to.
Yeah, exactly. State space
Oh,
conversion.
okay. Sorry, I don't have a saved document of that.
No
Not a
issues,
problem.
Abhinav. Some of us have taken it down here. We have noted it down. We can share it to Roshan. Not an issue.
Okay, just a
So
bit.
only one thing there is one. I think I probably I'm wrong or right. I don't know. But when you have written the matrix,
Huh?
in matrix basically. Uh, just let
Yeah,
me
I
get it.
have it. I'm sharing it. Just a second. So I have.
Just
Sorry.
yeah.
Yes, sir. This was the matrix I think I wrote.
Exactly. So
Yeah.
in this second term, like 2 1, what I mean to say, minus
So
LFCF plus
yeah,
matrix, first row, second column, second
yeah. This
row.
this one, right?
Yeah. So it Vx will come over here, na Abhinav. Minus Vx will come over here, na, if I'm not wrong. I think Vx you have missed over here.
Is it? Just me. Let me check once.
You see na, the first equation that you have written, Vy dot is equal to minus Cf plus Cr divided by mvx into Vy. In
Yeah.
bracket minus Vx plus CLF and plus CRLR divided by MVX plus CF into delta. Okay.
Oh, yeah. Here a minus Vx will come. Yeah.
So
Okay. Sorry.
I think it was missed now if I'm not wrong, right?
Yeah. Here there is a minus Vx term. Sorry. Yeah. That's
Okay,
true.
fine.
Thank you for
Thank you.
pointing out.
Thank you
So
so much.
here you can add a.
And second question I want to ask you, Avinav, that
Yeah.
I have tried to solve this matrix and all those things, but I was just getting lost in too many, like what I mean to say is variables. So the value of CF and CR and all those things, what you have given us in the table,
Hmm.
can you put over here or we have to just put afterwards? What do you recommend?
Because I mean this is essentially a theoretical, final output of the derivation.
Right.
So yeah, for solving purposes you can put before itself and solve it. But uh, actually, how the you if you want to understand the the interaction of parameters and all, how which is affecting which, then generally I'd recommend you come till here and then put the uh, the values.
Okay. Fine, Avinav. Thank you. So while solving it, I can solve by hand and put that handwritten note on the what I mean to say in
Yeah,
the.
sure. Whichever is easy for you. I just wanted to see that you are able to, derive this and then put the values and get the transfer function. That's all.
Cool. Thank you.
Whichever is easier for you, you can do that.
Cool. Okay. Thank you.
Yeah.
I'm sorry I just dragged you back. I'm sorry.
No. I'm thankful that you pointed out. Otherwise, I would have. Yeah. So coming back. Yeah, this change also please make in the document. The maximum peak overshoot, change it to less than 4%, right? Now, we'll move our poles. So, oh, sorry. Yeah, now we'll shift our poles to get, give the KP or the proportional gain. So we'll put it right at the margin. So we'll observe the characteristics, that is the peak response as well as the settling, I mean the steady state value. Okay. Final value is the same as 0.349, so we have no steady state error. That is fine. And the peak overshoot is 2.93%. So here so the peak deviation is 0.359, so that shouldn't be a problem at all, right? So we are well within the constraints. Now, so what is the KP value? Where is my KP value now? Can you see it?
Sorry.
Hello?
You have to just point on the point now, and it will reflect the value of KP if I'm not wrong, right?
Where should I point out?
Step response, the point that you have, yes, there. So overshoot.
This gives the characteristics of the plot, not of
Yeah,
the.
KP will be in this root locus domain, if I'm not wrong, right?
Okay, if I come here, where? So which block is responsible for giving the KP?
It's block C. And
Block
Can you go
C.
to the block,
what
please?
Yeah, so block C value is displayed here, right? So this is the value of KP.
Yes. Okay.
Understood? So the value of KP is 20.662 for this example. You may get a slightly different value because the parameter values are approximate, right? So now we'll go to the design of PI controller, right? So for the PI controller, we have what is the structure of the PI controller once we put the integral as well. So we have Kp plus Ki by S. So that when we simplify, we'll get Kp times S plus Ki by Kp by S. So I'll just write it down. I do I have that note here? Okay. I'll write it with the mouse only. Please forgive me. So the controller will be Kp plus Ki by S, right? This will be the transfer function of the controller once we have the PI controller. So this, when we take the LCM and I take Kp common, so what I'll get is I'll get S plus Ki by Kp. Okay, so is it clear how we got this form?
Yeah.
It's clear, right? So we took the LCM, it becomes S times Kp plus Ki. Then we took Kp out. So then we'll get this. We are getting it to this form. Why? What is the reason? So that in the root locus, so this directly shows once we have this transfer function, what we have to do is we'll have to add an integrator, that is 1 by S term, and we'll have to add a real 0. So that's why we are getting it to this form. All right. So now I'll go back to the MATLAB window. So now here I'll have to add one integrator, that is the 1 by S term, that puts a pole at the origin, and next I'll have to add a real 0. So once I select the real 0, the mouse turns like this to, which will allow me to select where I want the real 0. So I'll put it around like this. So now if you see, the plot is too much, it's settling after a very long time, so I'll want to make it more optimal. I'll take my real 0 much closer to origin, and you see my poles are in that shaded region, not in the white region. So now, okay, this seems a little bit okay, but still. So now this, so here you show, it shows the value of the C block, right? So this is the form, that is Kp plus Kp times S plus Ki by Kp by S. So to you see after the peak overshoot, it is settling after 2 seconds. So just imagine if the car takes 2 seconds to settle after you give the steering. So it is a very long time, right? So now we'll edit the compensator. Yeah, so this allows us to choose a reasonable value of the location of the real zero. So I think I'll if I when I move it closer to the origin, I'll get a much better value. So the overshoot is still a problem. So okay, now it is settling at a reasonably small time, but I have a
One. Abhinav,
steady state.
am I audible, Abhinav?
Yes, please tell me.
That small box next to C equal to is there, right? That you're entering 20. That is actually
Yeah.
the ratio of KI by KP.
Yeah, this value is this 20 value, right?
Yeah,
This
yeah.
is the gain. Yeah, you can say it as actually it is not ki by kp, it is kp by ki.
Okay, but
So if you see that it is 20 times 1 plus 2s by s. So in our form, when by kp was out, so here 1 plus remains the same, and
correct.
this 2 is the inverse of the location of the
Correct. I'm
real
able to
zero.
understand that. Yeah. So 20 into 2 is what is coming out as 40 in that window on the left
Yeah,
hand side.
yes,
Yeah, that is clear.
yeah. So when you change this gain, no, it will try to or else if you compare it with the form directly, you can see that this is actually
Yeah, I
ki.
compared to that format only, I saw it is KI by KP only, I believe, correct? That's
Yeah,
why.
I think it is ki by kp. Yes.
Yeah.
No, KI should be KI by KP should be 0.5.
KI by KP only, we are keeping it as 20 then in the problem.
Uh,
Is that how we have to proceed?
yeah. This value is not ki by kp. This value is of ki. I'm sorry.
KI only.
Yeah, just ki.
Okay.
Because when you
KP
multiply, it is 20 by s plus 40 by 40, right?
Okay.
So 20 by s term is the numerator is ki, just ki. All right. Is it clear
Okay.
now?
Yeah.
Okay, I'll proceed then. So now to increase the effect of so when I put my ki to be 40, the integrator essentially removes the steady state error, right? So the purpose of integrator is to remove the steady state error. So uh, when I put a value of yeah, so if I see here, now my peak overshoot is 19%. So and my steady state error is 0.349. So I don't have my steady state error, and my all my poles are, if you see all my you can see that all my poles are within the white region, right? So now I can freeze this. So the value of Kp. So from this, what I can understand is the value of Kp is Kp turns out to be 4, and is the overshoot too much, or the time second is 3. I'm sorry. Okay, the settling time is 3 is a huge value. So I'll change the location. This is a reasonably good value. Now, yeah, you can see that it is settling in 0.4 seconds, and the peak overshoot is also not much. But I have a steady state error. My value is 349.
Abhinav, I have a question over here. I'm sorry to
Yeah,
interrupt.
yeah,
Like you are moving this value of what I meant is location and sometimes KI, right?
yes, yes, yes.
So, sir, do you have any thumb rule of this, or it just comes from experience and practice? What is the funda behind this? How you're choosing this value, like
Okay,
minus
so
0.3, stuff
yeah,
like that?
so the basic thumb rule is once I have applied my K. First, I design the proportional controller, right? So then I get an insight of how much the value of Kp should be for only proportional controller, right? Then I understand what my Kp should be for just the proportional controller value. Then the location of poles will be one thing I know is that when I am optimizing this uh, controller, I know that the poles will be at the border, near to the border, right? So when I am designing the controller, what I'll see is whenever I am adding a real zero, one thing is I want to keep my poles in the white region. So the real zero will be very close to the origin so that the effect of the poles will be nullified, right? So one thing is the location of the poles will be closer to zero, and as you move, what I see is as I move the real zero closer, what is happening? What is happening to my plot? That I'll see, and then if for a given value of the location of the real zero, uh, as I change my this ki value, then how is my plot getting affected? Whether if you see earlier, there was a peak and there was a long stretch to get it to the settling value. So then what I did, I made my the location of real zero closer to the origin, right? That resolved my problem. So that's how you do it. You fix one value of location, you change this, see what happens, like that. Initially it will be like that, but as finally that's the point. As you practice and practice, you'll get the essence of, like, you'll get the intuitive feel of what these changes will do.
Thank you, Abhinav. Thank you.
Okay,
We
so
shall try, and if I'm not getting any value, I'll call you and get the values.
sure. So one thing is the construction of route array, right? That will help you in getting this. One thing is it will tell only whether it is going stable or unstable. So once we are in the stable region, you will have to play with the location of poles and zeros. All right. See, now I have, for these combinations, you can see that my poles are near the border, which is what I want. So now I am at a reasonably good value. See, my final value is 0.349, which is not different from what the step I gave, and my peak overshoot is overshoot percent is 4.23, which is peak overshoot. I'll have to reduce to 4, so below 4. Yeah, overshoot is now less than 3 point, 3.74. It's settling at 0.4 seconds. So now I can fix these values, right? So this is how you manipulate the location.
எல்லாரும் silent ஆ சொல்லிருப்பாங்க.
Abhinav, can you hear me?
Yes.
In that requirements where we are editing, I'm sorry, in the compensatory window, can you just open the compensatory window?
Yeah. Yes.
Sorry. Yeah. So how we have decided that integrator, I mean, since in that window I can right click and add another real zero, another real pole or whatever it is. How did we decide that it's only one real zero that we are adding right now?
We are adding a real zero because my transfer function says so. See, this is the controller transfer function, right?
Correct.
So we have only one real zero to be added. This s plus ki by kp is the term that is giving us the real zero.
And the nature of my transfer function that I have got is also mimicking this. That's for that reason only we are putting that way.
Nature of the transfer function in the sense?
Because I mean, we don't know the transfer function yet, right? Since you have given the transfer function, you are telling that it is only one s plus k by kp term that is there.
Yeah, we know the structure of transfer function. We know how many poles and how many zeros I am adding when I am adding a PI controller. We don't know the gains. I mean, we don't know the values exactly. But I know that I have, when I am adding a PI controller, I am adding one pole,
Correct.
and I am
One
adding
pole
a
and then
one
one
zero.
zero.
Yes.
Yeah. Okay, so the standard format is what we are going to refer always.
Yeah, standard format is, there is nothing else from this. When you
Okay.
add a
So
PI
any
controller,
KI, understood. Any KI by and any KP KI controller will involve this format and hence the.
Yeah.
Okay, understood. Okay, now again, can you go back to that window?
Yeah.
Avinav,
Here
sorry, Prem. Just to expand on the Prem queries, suppose I have a transfer function of plant is s plus a divided by s square plus ab, something like that, quadratic equation. So
Okay.
already we have a s plus a. That means numerator we have s plus a. That means already we have a real zero over there, right?
Yeah, those are already plotted when we give the transfer function itself. You see,
Oh.
there is zero here, right?
Right.
Why did this zero come?
Okay.
This
Got
zero
it.
is part of the transfer function.
I got it. Thank you.
Yeah.
Prem, thank you for asking
Yeah.
that question. It solved.
Yeah, understood. So Abhinav, just one question on that damping and frequency value as well.
Where is that?
I mean, that corresponding
here.
integrator and the real zero, we are having the values. What does that signify actually?
These values of damping and frequency.
Yeah.
This essentially tells, see, intuitively when you compare a system with a spring mass damper system, the omega n there, the omega n and zeta are directly what we deal with, right? But here this system is not a direct spring mass damper system. So here this gives the omega and the damping for this system. Okay.
I'm still not able to correctly understand, but
okay. So this is a second order system, right? This is a second order system, no? Because we, in our state space model.
Yeah. Second order system. Yeah.
So this second order system, if you think that this is a spring mass damper system, these are the damping and frequency that are coming because of adding these see, whenever you add a controller, you are changing the damping and frequency. That's what you are doing with the controllers.
Okay.
So whenever you are adding this integrator, because of this integrator, you are affecting the damping in this way and frequency in this way, and real zero is affecting like this and frequency like this. That's what it signifies.
I'm able to understand, but the values is what I was trying to understand. -1 and 1 and all. Why specifically those values are coming? But it's because of the mathematics. Understood.
Yeah. I am not exactly sure about what these exact values signify. Maybe I'll see and get back to you if I get something.
Sure, Abhinav. Thank you. Please
But this
continue.
is a theory behind it. So
Yeah,
essentially,
understood.
yeah, okay.
Yeah, yeah.
So now, so we are well within the constraints. We have my peak overshoot. I mean overshoot below 4%, and the final value of 0.349. So I have no deviation at the final value, and my settling time is very reasonable settling time. So now I can freeze this KP and KA values. So now the next part is the one with the steering actuator dynamics. So where is that? Yeah. So there is my steering actuator dynamics. What happens is, because of this dynamics, this essentially goes, along with the transfer function of my the lateral dynamics transfer function, whatever I'm working with. So till now I'm working with just this, but now because of this actuator dynamics, I'll have another transfer function, and for this combined system now I'm designing a KP and KI. Is it clear the effect of including the steering actuator dynamics?
Sorry, Abhinav, can you repeat? We couldn't hear.
Yeah. So the steering actuator dynamics is like essentially modeling the relation between the steering wheel and the tire of the wheels of the vehicle. So
Correct. We can say that it's a lumped model modeling the rack, all those things together.
yeah,
Very good.
you have the rack and pinion, and if we have
Yeah.
power steering and all those things come,
Correct.
this transfer function is directly modeling that. Now when
Okay.
we include the steering actuator dynamics, our transfer function, which we are dealing till now, we are dealing only with this, or just the bicycle model.
Yeah.
Now what happens is our steering dynamics also come into play, and now we are designing a controller for the entire system, a combined system.
Got it.
All right.
Yeah.
So
And
I'll
still here also we'll maintain the same desired heading angle of 20 degree only.
yeah, the constraints will be same. All these things
Okay.
we won't change. You'll have to do the same exercise with the change transfer function.
Okay. Yeah.
All right. So I'll leave that to you. If there are no more doubts, we can close the session. In the report, what are to be included are all given here. The main changes I'm repeating again. You need not include the Bode diagram, and one more thing is the
Overshoot correction
is less than 4%.
4%.
Yeah,
Yeah.
those are the only ones.
Abhinav, today the MATLAB online session was having some issues. It was telling that server issues are all there, and then some errors are popping up. We'll try again and we'll get back to you probably.
Yeah, no problem. You can mail me whenever you have a doubt, and I'll try to answer.
Yeah, thank you.
So, and when is your end semester exam of this course?
May 9th.
May 9th, right? So, can we put the deadline next Saturday on 26th or Sunday or 27th?
Yeah, it's okay.
Oh, okay, Abhinav. Yeah.
Okay. Is it fine?
Yeah.
Good. Okay. So I'll put the deadline update the deadline in the Google Classroom as well. So 27th end of the day will be. You can always reach out to me through email, or if it's urgent through phone, I'll try to answer the question.
Sure.
Thank you, Abhinav.
Yeah, and I'll try to elaborate more on the damping and frequency, what exactly those values represent. I think who asked that? Prem, sir, I think.
Prem here.
Okay, sure. I'll try to mail that once I get it.
Sure, Abhinav. Thank you.
Okay.
Thank you, Abhinav.
Thank you very much.
Yeah, thank you, Abhinav.
Meet us when we come to IIT for writing exams. Okay.
Yeah, sure. I'll be the invigilator like last time.
Thank you, Abhinav.
Thank you.